Welcome back to this course on Fundamentals of Computer Architecture. The topic of this lesson is Amdahl's law, which is a fundamental equation in computer architecture. The previous lesson I told you that computer architecture is not rocket science and that there are not many equations you need to memorize. The CPU performance equation is one you should know, but here's another one. It is known as Amdahl's law. In my opinion, you don't have to memorize it. I don't memorize it. Instead, you should be able to visualize and derive it. Here's what I mean. Suppose our application is executed on one processor core. Suppose also that a fraction of, let's say, S of the total execution time is completely serial and that a fraction of, let's say, F is perfectly parallelizable. Completely serial means this fraction, this part of the total execution time, cannot be accelerated in no way whatsoever. On the other hand, perfectly parallelizable means that this part of the total execution time can be parallelized with perfect linear speedup. By definition, S plus F equals 1. Now we execute this application on two processor cores. Then the execution time will look like this. A perfect speedup of 2 is achieved for the parallelizable part, but the serial part remains the same. Similarly, when we execute our application on 3 or 4 or 1 million cores, the parallelizable part of the total execution time will shrink, will become tiny forever, but the serial part will not become any smaller. This observation led Jean Amdahl, who is shown here, to conclude in a famous scientific paper that if, for example, 50% of the execution time is sequential, the maximum speedup you can get is 2, no matter how many cores you use to accelerate the parallel part. Actually, he didn't use the term cores, but processors, because cores is a term from the multi-core era, and he wrote his paper long before. In general, the time on one core is S plus F equals 1, and the time on P cores is S plus F divided by P. Speedup is the time on one core divided by the time on P cores, and this is equal to 1 divided by S plus F divided by P. Since S plus F equals 1, or S equals 1 minus F, this is equal to 1 divided 1 minus F plus F divided by P. This is the equation known as Amdahl's law. An immediate consequence of Amdahl's law is that performance is limited by the serial fraction. If S is the serial fraction, the speedup is limited to 1 divided by S. For example, if S is 10%, the speedup is at most 10, and when S is only 1%, the maximum speedup is at most 100. This figure shows the speedup calculated using Amdahl's law as a function of the number of processor cores for different parallel fractions. 50%, the purple line, 75%, the green line, 90%, the red curve, and 95%, the blue line. The vertical axis shows the speedup, while the horizontal axis shows the number of processor cores. Please note that we use a logarithmic scale for the horizontal axis. It can be seen that the speedup is determined more by the fraction that can be parallelized than by the number of cores. In fact, even though we use more than 16,000 cores at most, the speedup is never more than 20. Amdahl's law assumes implicitly, however, that the problem size and problem complexity stay the same when we use more cores. In most cases, however, we use more cores to solve bigger and more complex problems. There is also a related law known as Gustafson's law, which states that the runtime, The total execution time stays constant when we increase the number of cores. This, however, is the topic of another lesson. Amdahl's law was originally formulated, like I did too, as the maximum speedup that can be achieved with p cores. But it can be easily generalized to any improvement due to any source. Assume, for example, that we can improve small f of the total execution time by a factor big F. What will then be the speedup, the overall improvement? Again, we can draw a figure as before. The green part corresponding to a fraction of small f is the part we can improve. The red part corresponding to a fraction of s equals 1 minus small f is the part we can not improve. The overall speedup is then given by 1 divided by s plus small f divided by big F. This is exactly the same equation as before, except that s now corresponds to the fraction we cannot improve, and small f equals 1 minus s corresponds to the fraction we can improve, and big F corresponds to the factor with which we can improve the improvable part.
This concludes this lesson. Thanks for watching. In the next lesson I will give some examples of Amdahl's law. Stay tuned.